And so that's B2 in those cases. There's other particle in a box things that I'll go over, right? So, the 3D one we'll talk about, and then there's also the 1D ones as well. So hopefully we'll be able to get to those. Awesome, pen's back. Okay, A3. This is a 1D particle in a box problem, right? So if we imagine a dot of ink, right? So we've moved away from we're not doing this problem related to an electron, right? We're just simply talking about a single dot of ink, right? It has that mass, 0.113 nanograms. It's trapped in a 10 centimeter box, right? It's basically a length of paper. Well, not like legal paper, but like like a small like A5 paper. Right, we can do a particle in a box thing, right? And that one ink of dot, right, is actually like how much the mass, right? If you're using an inkjet printer, right, like it spurts out like little inks, dots of ink, and stuff, right? Like one of those dots has about that mass. So if you were to like be like, oh well, what if that dot of ink could travel along a piece of paper? Like, what's the deal? So that's what we're doing here. So the first thing, right, is to do the dimensional analysis of the particle in a box problem, right? And the whole purpose of this exercise was to make sure and re-emphasize that you guys understand what the units have to be for everything that gets plugged into the equation, right? Because it's easy enough to be like, okay, we're at a nanogram, we're at a centimeter, right? That's a mass, and that's a length. Let me just plug that in there, right? You're not going to get a correctly scaled energy value, right? Because everything is just off in those cases, right? And so the way to approach this, right, is that we have the equation right here, right, for energy. So we have energy is equal to n squared times h squared over 8ml squared, right? So if we just simply write out what the units for everything are, we know that n, right, is unitless. There's no units for it. H, right, is joules seconds squared, or joule seconds, right? And then that whole thing gets squared, right? We have 8 times mass, right? So the mass should be in kilograms, right? And then the length should be in meters, right? So that's then meters squared in this case. So looking at it right on its face, that isn't going to inspire you with much confidence in terms of, being able to do the dimensional analysis to get it to be just simply an energy unit, right? Which in this case should be in joules, because, nothing really seems to cancel out, right? None of the units are the same on either, top or bottom, like at its face value. The thing that you have to know, right, is that a joule is equal to a kilogram times meter squared over second squared, right? That's in SI units, right? That's what a joule is, right? If you were to break it down further. So if we take that value, right, and we plug that into our equation that we have, right, what we get is, right, and so I'm just going to completely drop the unit list because that doesn't matter, right? So then what we have then is kilograms times meter squared times seconds, right? So I'm just going to have the seconds there over second squared. This whole thing becomes squared, right? And then we have 8, right, which doesn't matter because it doesn't have a unit, times kilograms times meter squared in this case. So we have that right there. So now, right, we just square all of this stuff out. So what we get is that energy is equal to kilogram squared times meters to the power of 4 times second squared over seconds to the power of 4 over, or actually, let's put it all on the same line, over kilograms times meters squared times seconds to the power of 4. Right, so we have all of this. So now everything is like a unit that we're comfortable using and looking at, and so all we have to do is just start, scale, having things cancel out, right? So the square cancels, that kilogram's gone, right? This becomes squared, right? This is gone, right? This is gone. This becomes squared. So now what we have as our unit is kilograms times meter squared over second squared, which is the exact same thing as a joule, right? And that's how you get, through dimensional analysis, that equation that initially looked as if nothing would cancel out to something that cancels out to being into joules, right? And that's why the energy is in joules in this specific case, and why you have to make sure that your mass has been, converted into kilograms, and that the length of your box has been converted into meters, right? Those are the important parts. Next part. So, B and C, right, is asking to sketch the wave function and the probability, right? And so these are just simply things, right? You can go through the whole process of plotting all of them into to computer programming and copying it over. But the easiest way to think about it is, with every n level, right, you start to increase the number of nodes. And so just like as I mentioned right when I was talking about the problem earlier, the number of nodes in these wave functions is going to be n minus 1, right? So if you have, if you're at the n equals 1 energy level, right, there's 0 nodes. And so the way that wave looks like is just simply like this. Right there, right? It's just simply a hump. There's no node. Right? If you go to the n equals 2 level, right, you're going to have one node, right? Because n minus 1 is equal to 1. And the thing, right, is the node is always going to cut up that wave so that it's in equal parts, right? So that there's always like an equal amount of the wave is on the left side of it as there is on the right side. So that means then that, the node is going to be right there. And so we can just draw this right there. Right, n equals 3 is going to have 2 nodes, so that gets cut up, so we have 3 parts to it. So right there's going to be one there, right? N equals 4, 3 nodes in this case now, and so there's going to be like 4 hills and valleys, right? So you're the easiest way to do it, right, is because there's going to be 3 of them, right? One of them is going to be in the middle, and then one's going to be cutting in those other 2 halves, and so you can just be like boop 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 boop. In those cases, right, n equals 5. So now we're going to have 4 nodes in this case, right? So it's like 1, 2, 3, 4, right? And just simply, right? And so that's what the wave functions look like. I don't go to RISD, so I'm not like the best at drawing or anything like that, right? But that's a pretty decent, pictorial representation of where everything is. And because we know that both sides are all going to be the same, we know that in terms of the nodes, right, this is at L over 2, right? It's going to be at the halfway point, right? We know because we're cutting everything up that this is going to be right at 1/3 L, right? This is going to be at 2/3 L, right? This is going to then I'll cut this up, so we're going to have L over 2, L over 4, right? 3/4 L in that case, right? This is all going to get cut up, so you have in these cases, right, it's all divided by 5, right? So this is 1/5, right? 2/5, 3/5, 4/5, right, and so forth. Right. So that's how all of them get cut up, right? So that's what the wave function looks like. And so then in terms of what the energy the amplitude should be, right? Just thinking back to what we understand from trigonometry, right? This right here is just simply the amplitude. So in this case, right, you get the square root of 2 over L, right? And that's going to be the same in all of those instances. If we were to go now and do the probability, right? The probability is just simply the system squared. And so again, right, if you were to do that, the easiest way to think about it is that it kind of has this like, Gaussian shape, right? Where it like has, if you've ever seen like a bell curve or anything like that, right? It just simply is a bell curve for all those different parts. And so it doesn't matter what the phasing is, the probability is always going to be positive, but you can always expect, the halfway point, right? The maximum of that hill or that value is always going to be the maximum point of the probability. Right. And then things are going to taper off. And so then in this case right here, right, you just simply get, something that looks like this. And then here you get, 2 bell curves, right? Because, the maximum here and, the maximum right there, right? And the same thing here, right? These guys, look like that right there. These guys, again. Right, and so that's what the probabilities look like in all of those instances, and everything. So, and then because we're squaring the wave function to get the probability, right? The amplitude is simply then 2 over L in that case, right? Because if it was square root of 2 over L as the amplitude beforehand, right now, it'll be 2 over L, right? And that's how you plot these, the 1Ds, in terms of both the wave function and the the probabilities, right? That's the easiest way to approach it, is just simply think about how many nodes are you expecting, right? You know that everything's going to get cut up equally, and then just like, just drawing waves and stuff. So, all right, D, right? Calculate the energy of each level, right? So for this one, right, it's just simply this equation right here that we're going to be using. So it's E is equal to n squared h squared over 8m L squared. So we know that H, right, is 6.626 times 10 to the negative 34 joule seconds, right? So in this case, M is going to be equal to the mass that we had mentioned have at the beginning of the problem, right, which is 0.113 nanograms, 0.113 nanograms. So if we convert that into kilograms, right, that scaling is, right, so you have, there's, right, so if we take this, and so we have 1 gram, right, is 1 times 10 to the negative 9 nanograms, and we know then that 1 kilogram is equal to 1,000 grams, right? So then that means that the mass in this case is 0.113 divided by 1 times 10 to the negative 9 divided by 1,000. Oh, no, not times 1 to the negative 9, right? It's 1 times 10 to the 9 nanograms, right, is 1 gram. And then 1 kilogram, right, is 1,000 kilograms, yeah. Or not kilograms, grams. Let me do this again. All right, so yeah, so 0.113 times 1 divided by 1 times 10 to the negative 9 gives us 1.13 times 10 to the negative 10 grams. To convert that into kilograms, right, we divide that by another 1,000. And so what we get then is that the mass of the ink dot in kilograms is 1.13 times 10 to the negative 13 kilograms. Now the length, right, I think I said it was 10 centimeters is what the box was. Yeah, 10 centimeters. Right, so 10 centimeters is, right, 1 meter is 100 centimeters, and so that comes out to being 10 divided by 100 is 0.1 meters. In this case, right? So now everything is in the scaling that we need it to be. And so now all we have to do is just simply plug and chug everything. So the easiest way to approach this, and I had mentioned this in the particle in a box video, right, is that because all of these values are going to be exactly the same no matter what the energy value is, we can just calculate that part first, right? So if we're looking at the energy value for when n is equal to 1, right, h squared is 6.626 times 10 to the negative 34 joule seconds squared over 8 times the mass, which is 1.13 times 10 to the negative 32 kilograms, times the length, which is 0.1 meters in this instance, right? And then all of that's going to get multiplied by 1 squared. And so the first part of it is just simply, right, 6.626 times 10 to the negative 34 squared divided by 8 times 1.13 times 10 to the negative 13 times 0.1, right? So this comes out to being 4.86 times 10 to the negative 54. Let me make sure that that's what I have here. Something is slightly different. Oh, I forgot to square the length again. Yeah, there we go. Now it's in negative 53. Yeah, so we got 4.87 times 10 to the negative 53 joules, right? So that's the energy level for 1. And so this value right here, right, is just simply all of that. And so all we have to do then is just simply take that value to make our lives a lot easier, right? Is we can just simply do E1 times, right, 2 squared to find out what it is for the n equals 2 level. right? So that comes out to being 1.94 times 10 to the negative 52 joules, right? And you can just work your way through that way, right? And that's how you calculate all the different energy levels, especially like a quick way to do all of the different ones. E, right, is determine the probability. And so I had mentioned this before. You can just do this pictorially, right? You don't have to go through, doing calculus or integrating or anything like that. You just have to know what regions you're looking at. So for the first part, right, if we know that the length of the box, right, is 10 centimeters, right, we know that this is from 0 to 10 centimeters. And so the first question is asking, right, from the 7.5 to the 10 centimeter region, right? So then that means the half point here is 5 centimeters. And that means then that this is 7.5. And so if that's the case, use orange, right? Then that means that what we're looking at for the n equals 2 level, right, is this region right here. And so because we can break it down, we know then that this whole part right here is 50% probability, right? Because it's the halfway point, and you have those two parts right there. And we're even cutting that even further, right? Where we're cutting that probability in half once more. And so that comes out to being then, right, 25%. Excuse me. In these cases. Right, we can then do the next thing, right? We're then going from the 0 to the 5 for the n equals 3. So we're looking at going from here. So we're looking at the probability of all of this. And so we know then that each one of those humps is a third. And so if we were to, right, so we already know that that first hump is 33%. The second hump there, right, we're cutting that one directly in half. And so cutting that in half, right, half of 33% is like 16.7, right? 33 plus 16.7 or whatever, it comes out to, being basically 50% in this case, right? So that's 50% here, right? If we go now from the 2.5, so this is, that's the 2.5 centimeter region to the 5 centimeter region for n equals 4, right? So we're going from this point right here, so that would be 2.5 to here, right? So we're looking at this part right here, right? So we know that each one of those humps is 25% probability, right? Because the full percentage is 100. If there's 4 of them, right, that's a quarter, right? So that becomes 25% probability. And then the last one, right, we're going from the 0 to the 6, right? And so that would be this point right here. So we're looking at the probability of those 3 humps. And so we know that each one of those humps is worth 20%, right? Because each one of them is a fifth in those cases. So we just simply multiply each one of those by 3. And so what we get then is 60%. Which I think is right what I have here. Yeah, 60%, 25%. Yep, exactly. So that's how you essentially you can eyeball your way through the probabilities. All right, so last part of the problem, right, is, without performing any calculations, describe how shortening the length of the box to 2.5 centimeters will impact the energy of the various n levels. How would reducing the ink dot from a collection of molecules to a single molecule, right? And so the way to think about it is, you don't have to do any calculations. You just know, right, if you're going from 10 centimeters to 2.5 centimeters, you're cutting the length of the box, down to a fourth of its original size. Looking at the equation for the energy, right, this guy right here, we know that the length of the box is in the denominator, right? So if the denominator becomes smaller, then that means that the total energy then increases, right? Because mathematically wise, right, a smaller denominator is always going to give you a larger number in the end. So if we're going down a quarter of the size, right, we would expect it to then increase at least by 16, well, not at least, right, it's going to increase by 16 times, right, because the L, right, is squared, right? And so if we're going down a quarter in those cases, right, that gets squared, right, that's 1 over 16 then in those instances, right? So 1 over 16, then that means that has to translate into a 16-fold increase in the energy in those cases, right? And that's without doing any calculations, right, we can just simply see that. And at a minimum, right, just simply saying, be like, okay, right, it's going to increase in energy if you shorten that box, which is true. And then, right, if we go then from, the ink dot If we're going from the collection down to a single molecule, right, it's going to be the exact same thing, right? Because again, the mass of the particle is in the denominator, and so if that mass increases, or sorry, that mass goes down, right, which would happen if you're going down by 5.7 times 10 to the 15 molecules, down to a single molecule, then right, you would then expect it to be that same inverse relationship, where now if you're going down to that small of a mass, you'd expect the energy to increase by that same amount, in those cases. So right, and that's just simply looking at the equation and looking at like what's the relationship there between the two of them.